Good day. My name is Oscar Daniel Luperzo Madero, and I am currently enrolled in the Master of Engineering and Materials Science program. The presentation will entail the exposition of a scholarly paper bearing the title Study of the Influence of Reinforcing Particles on the Crystalline Structure and the Elastoplastic Behavior of Titanium and Titanium Diboride Composites for Mechanical Biocompatibility in Medical Devices. This work was developed under the direction of Dr. David Bravo Barcenas, a researcher at FE-SEM, City for Mexico, who was assigned to the University of Guadalajara. As a first, metallic biomaterials are of particular importance in the field of material sciences applied to medicine, especially in the domain of orthopedics, where they are employed to restore motility. The metals must be biocompatible because no adverse reactions in the host tissue and exhibit high resistance to corrosion and wear. The most commonly used metallic biomaterials include AISI 316L stainless steel, chromium cobalt alloys, and commercially pure titanium, with titanium standing out for its mechanical properties and greater corrosion resistance. Titanium has low Young's modulus and low density, characteristics that are valuable for prosthetics. However, the prosthesis' lower hardness and wear resistance can cause deterioration due to friction with bone tissue. The incorporation of ceramic reinforcements in the composite results in the formation of metal matrix composites, thereby enhancing the properties of the composite. In the field of material science and engineering, titanium carbide, titanium boride, titanium nitride, and titanium diboride are among the most commonly used reinforcements. Of these, titanium diboride is particularly noteworthy due to its ability to diffuse into titanium matrices, forming titanium boride interfaces that enhance load transfer and topological properties. In the process of sintering material matrix composites through the medium of powder metallurgy, the phenomenon of porosity is introduced, which has the capacity to reduce the material's Young's modulus. H. Ottar and collaborators compared the mechanical properties of commercially pure titanium parts and metal matrix composite systems composed of titanium and titanium boride, produced via selective laser melting, casting, and powder metallurgy. 3 samples were sintered using powder metallurgy with the compaction pressures varying only as consequence of the process. The low concentration of reinforcing phases appeared to favor the formation of titanium diboride whiskers in the titanium matrix. The objective of this study is to ascertain the impact of incorporating titanium diboride into the commercially pure titanium matrix during the sintering process with regard to its structural, microstructural, and elastoplastic characteristics. In order to prepare each composite, a mixture of commercially pure titanium grade 1 powders and titanium diboride particles was created, with varying concentrations of the former component ranging from 0 to 15% by volume, and the latter from 0 to 10% by volume. The mixtures were subjected to a compaction furnace at 10 to the power of -4 millibars. The heating ramp commenced at a room temperature and increased at a rate of 5 degrees Celsius per minute until reaching 1,300 degrees Celsius, where it was maintained for a duration of 2 hours. The composites were subjected to cooling within the furnace. In order to ascertain the crystalline structure, a pananalytical impedance diffractometer with a copper K alpha source, where lambda equals 1.54 angstroms, was utilized, with a sweep rate of 2 degrees per second over a range of 20 to 90 degrees into theta. For microstructural characterization, a Nikon Eclipse MA100 optical microscope was utilized to obtain microphotographs of the samples under visible light. In order to characterize the mechanical properties, vigorous microhardness and nanoindentation tests were performed. The microhardness of the samples was evaluated using a microhardness tester FM800 with a Vickers type indenter. The test parameters include a load of 500 grams force applied for 15 seconds, with 30 indentations per sample, in both the longitudinal and transverse directions. The nanoindentation tests were performed using NanoVea CV500 nanoindenter, with a normal load of 100 millinewtons, a loading and unloading rate of 200 millinewtons per minute, and the Berkovic type indenter. The samples were subjected to 30 indentations in each direction, longitudinal and transverse. As illustrated in Figure 3, the initial powders exhibited a specific morphology, and the phases present within them were identified as pure. This confirmed the absence of any contaminant phases. Furthermore, the X-ray diffraction patterns of the sintered samples are presented. The compounds demonstrate that the alpha titanium phase is the most prevalent in these sintered systems. In the case of reinforced compounds, they also exhibit characteristic peaks for titanium diboride and titanium boride, phases that increase as the amount of reinforcing particles increases. As illustrated in Figure 4, the micrographs of the sintered samples reveal the presence of a distinct phase. The composites containing 3, 5, 10, and 15% by volume of titanium diboride exhibit the formation of whiskers in their microstructure generated by the reinforcing particles in the matrix, in addition to the presence of the coaxial grains of the alpha titanium phase in all samples. As illustrated in Figure 5, the outcomes encompass the relative density of the samples, the behavior of the beaker's microhardness, and the analysis of variance analysis of the elastoplastic property results for each sample in relation to the addition of reinforcing particles. It is evident from the relative density data that there is a decrease in this physical property as the concentration of reinforcing particles increases. In addition, the beaker's microhardness displays an inverse correlation with relative density. As the concentration of reinforcing particles increases, this mechanical property also increases, reaching a maximum value of approximately 180 beakers hardness. The results obtained from the nano-indentation test indicates a nanohardness behavior similar to that of the beaker's microhardness test, with a gradual increase in nanohardness with respect to the percentage of titanium diboride. It is evident that the reduced elastic moduli decrease in proportion as the titanium diboride concentration increases. Concurrently, the ratio of nanohardness to reduced elastic modulus represents an elastic strain to failure, and the ratio of nanohardness cubed to reduced elastic modulus squared, representing yield pressure increased with the rising titanium diboride concentration, indicating an enhanced resistance to adhesive wear. In conclusion, the X-ray diffraction patterns demonstrate the presence of characteristic peaks of the alpha titanium phase in all compounds, as well as the existence of the titanium boride phase in the reinforced compounds, resulting from the diffusion of boron derived from the titanium diboride reinforcing particles into the titanium matrix. Microscopic images of the materials containing 3, 5, 10, and 15% by volume of titanium diboride reveal the formation of whiskers caused by the presence of the reinforcing particles. The beaker's hardness measured in the unreinforced samples exhibits the lowest value, and the gradual increase in hardness is observed with increasing titanium diboride content. This phenomenon can be attributed to the beneficial role of ceramic particles in enhancing the distribution of applied stresses throughout the matrix. It is noteworthy that composites containing 1 to 10% by volume of titanium diboride do not exhibit a substantial difference in their mechanical properties. Nano-indentation tests reveal no significant disparities between the nanohardness and is analogous to that found in the beaker's hardness tests, with a gradual increase corresponding to the higher titanium diboride content. As the content of titanium diboride increases, the elastic modulus of the composites decreases. This phenomenon can be attributed to the higher titanium diboride content, promoting the formation of pores during the process of powder metallurgy sintering. The presence of those pores leads to a reduction in the elastic modulus of the composites. Finally, the nanohardness to elastic modulus ratio and the nanohardness cubed to elastic modulus squared ratio show a gradual increase with higher reinforcement content, which, based on trends observed in the literature, suggests an increase in resistance to adhesive wear.